We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
I feel the liftoff. The clock has started. Roger.
This is a new and strange environment at first. Just suddenly finding yourself in orbit.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11. Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 38 of the Space Rocket History Podcast. And now, Syncom 123 and TIROS 8. Syncom, spelled Syncom, stands for Synchronous Communications. The NASA program began in 1961 for active geosynchronous communication satellites, all of which were developed and manufactured by Hughes Space Communications. Just in case you've forgotten, a geosynchronous orbit is an orbit around the Earth with an orbital period of 1 day. In other words, it matches the Earth's rotation period. The synchronization of rotation and orbital period means that for an observer on the surface of the Earth, an object in geosynchronous orbit returns to exactly the same position in the sky after a period of 1 day. Geosynchronous satellites have the advantage of remaining permanently in the same area of the sky as viewed from a particular location on Earth, and so permanently within view of a given ground station. The first 3 Syncom satellites were virtually identical. Each satellite was 71 centimeters in diameter, 39 centimeters high. It was in the shape of a cylinder or a can. The fully fueled mass of the spacecraft was 68 kilograms. The nozzle of the solid propellant apogee motor extended from the bottom of the cylinder, and a coaxial slotted array communications antenna from the top. The apogee motor could provide 1,000 pounds of thrust, and it was designed to increase velocity 1,431 meters per second. The total height, including the nozzle, was 64 centimeters. The radial exterior was covered with 3,840 silicon solar cells, which provided direct power of 29 watts, the 99% of the time that the spacecraft was in sunlight. Nickel-cadmium rechargeable batteries provided power when the spacecraft was in the Earth's shadow. There was no active thermal control required. Most of the central interior of the spacecraft consisted of the tanks and combustion chamber for the apogee motor. Around this were arranged 2 hydrogen peroxide and 2 nitrogen tanks and the electronics. Attitude and velocity control was provided by nitrogen jets to align the spin axis and hydrogen peroxide jets to position the satellite. Each system had 2 jets, one parallel and one perpendicular to the spin axis. Syncom 1, 2, and 3 used a redundant frequency translation active repeater communication system designed to handle 1 two-way telephone or 16 one-way teletype channels. Selection of the receiver and transmitter were made by ground command. One receiver had a 13 megahertz bandwidth for TV transmission. The other had a 5 megahertz bandwidth. The slotted dipole transmitting antenna radiated a pancake-shaped beam 25 degrees wide, and there were also 4 whip antennas oriented normal to the spin axis for telemetry and command. The launch vehicle for Syncom 1 and 2 was a Thor Delta B, also known as a Delta B. The first stage was a Thor missile in the DM-21 configuration, and it was capable of delivering 172,000 pounds of thrust. The second stage was the Delta D, which was derived from the early Delta. And the third stage was an Altair solid rocket motor, and it was capable of delivering 2,760 pounds of thrust. Syncom 1, also known as Synchronous Communication Satellite 1, was designed to be the first test of a communication satellite in geosynchronous orbit. The objective of the mission was to put the satellite into a 24-hour orbit with an inclination of about 30 degrees over the Atlantic Ocean. On February 14, 1963, Syncom 1 was launched into a highly elliptical orbit. Initial communications tests conducted from the United States naval ship Kingsport off Nigeria were successful. About 5 hours after launch, the apogee motor was commanded to fire to place the satellite into a near synchronous orbit. At about the time the motor completed its 20-second burn, all contact was lost with the satellite. NASA assumed that the satellite's spin axis was misaligned at the time of the apogee motor firing. Attempts were made to communicate with the satellite, but contact was never reestablished. Because of this, NASA was unable to determine exactly what the problem was. On March 4th, Syncom was spotted from the ground at the Bowden Observatory in South Africa. The spacecraft's initial orbit was computed to be 34,186 kilometers to 37,021 kilometers with an orbital period of 23 hours and 46.5 minutes. Many experts give Syncom 1 the title of the world's first synchronous communications satellite. Personally, I disagree. Syncom 1 acquired geosynchronous orbit, but it did not perform the function of a communications satellite. To me, that title belongs to Syncom 2. The nearly identical Syncom 2 was launched from Cape Canaveral on July 26, 1963, using a Delta B launch vehicle. The Delta B inserted Syncom 2 into a high-altitude orbit. 6 hours later, the apogee motor was fired to place the spacecraft in an orbit ranging from 34,000 to 36,000 kilometers with a drift rate of 7.5 degrees per day eastward. The apogee was then raised and the drift rate changed to 4.5 degrees per day westward toward the desired position over 55 degrees longitude. After 2 weeks of drifting, the nitrogen jets were pulsed in a series of 4 firings to slow the spacecraft to near zero drift on August 16th, followed by an alignment maneuver. The final maneuver put Syncom 2 into a geosynchronous orbit with an inclination of 33 degrees over the Atlantic Ocean and Brazil at the 55 degrees longitude. Syncom 2 began regular service on August 16, 1963. Voice, teletype, facsimile, and data transmission tests were successfully conducted between the Lakehurst, New Jersey ground station and the U.S. naval ship Kingsport while the ship was at sea off the coast of Africa, and television transmission were relayed from Lakehurst to the Telstar ground station at Andover, Maine. In August of 1963, President Kennedy in Washington, D.C. telephoned Nigerian Prime Minister Balewa aboard the Kingsport, docked in Lagos Harbor. It was the first live two-way call between heads of governments by satellite. Syncom 2 demonstrated the feasibility of geosynchronous satellite communications and earned the title of the first geosynchronous satellite. Which brings us to Syncom 3. While Syncom 2 was in a geosynchronous orbit, it was not in a geostationary orbit. The orbit was inclined at 33 degrees, so it moved in the sky in an elongated figure 8 pattern, 33 degrees north and south of the equator. Syncom 3's objective was to be the first geostationary satellite. You may recall a geostationary satellite has a circular geosynchronous orbit directly above the Earth's equator. Geostationary satellites have the special property of remaining permanently fixed in exactly the same position in the sky at all times, meaning that ground-based antennas do not need to track them, but they can remain fixed in one direction. A modern example is a TV service provider like DirecTV or Dish Network. I'm sure you realize if you have one of these satellite providers, your dish antenna remains in a fixed position because it is receiving from 1 to 3 satellites in a geostationary orbit. You don't have to move the dish to track the satellites. Syncom 3 was almost identical to Syncom 1 and 2, but the launch vehicle had to be upgraded in order to place Syncom 3 into a geostationary orbit. The launch vehicle chosen was the Delta D, also known as a thrust-augmented Delta. The first stage was a Thor with 3 Thiokol Castor 1 solid rockets strapped around its base. When the liquid and the solid fuel engines were ignited, the first stage could produce 332,000 pounds of thrust. The second stage was a Delta D, capable of delivering 7,575 pounds of thrust. The third stage was a Hercules solid fuel rocket motor, capable of delivering 2,755 pounds of thrust. On August 19, 1964, Syncom 3 was launched into an elliptical orbit, inclined 16 degrees to the equator, following a third stage yaw maneuver. The apogee motor was fired to remove most of the remaining inclination and to provide a circular, near-synchronous orbit of 35,670 kilometers by 35,908 kilometers. The spacecraft next carried out a series of altitude and velocity maneuvers to align itself with the equator at an inclination of 0.1 degrees and to slow its speed so it drifted west to the planned location of 180 degrees longitude, where its speed at altitude was synchronized with the Earth over the Pacific Ocean. These maneuvers were completed by September 23, 1964. Syncom 3 was then used in a variety of communication tests, including the transmission of the 1964 Olympics from Tokyo to the U.S., transmissions between the Philippines via U.S. naval ship Kingsport and Camp Roberts, California, and teletype transmissions to an aircraft on the San Francisco-Honolulu route. Satellite operations were turned over to the Department of Defense on January 1, 1965, and Syncom 3 was operated by the DoD through 1966. It was finally shut down in April of 1969. Syncom 3 remains in geostationary orbit, but over the years it has drifted 8 degrees to the west to longitude 172. Although Syncom 3 is sometimes credited with the first television program to cross the Pacific, I'm sure everyone recalls from episode 36, the Relay 1 satellite was the first broadcast television from the U.S. to Japan on November 22, 1963. And now, TIROS 8. You may recall from episode 20, the television infrared observation satellite program called TIROS was NASA's first experimental step to determine if satellites could be useful in the study of Earth. The TIROS program also tested various design issues for spacecraft, such as instruments, data, and operational parameters. The objective of TIROS 8 was to continue research and development of the meteorological satellite information system and to flight test the new automatic picture transmission camera system. Similar to previous TIROS satellites, TIROS 8 was 42 inches in diameter, 19 inches high, and weighed 270 pounds. The craft was made of aluminum alloy and stainless steel, then covered by 9,200 solar cells. The solar cells served to charge the nickel-cadmium batteries. 3 pairs of solid propellant spin rockets were mounted on the base plate. But TIROS 8 was unique from the previous TIROS satellites. It contained 2 wide-angle camera systems, one with the standard TIROS wide-angle lens and one with an automatic picture transmission lens designed to photograph an area 800 miles wide, which at the time was the largest field available. The launch vehicle for TIROS 8 was a Thor Delta or a Delta B, the same type of launch vehicle used with Syncom 1 and 2. On December 23, 1963, TIROS 8 was successfully launched from Cape Canaveral. Here's the audio.
8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. We have ignition. We have liftoff. We have liftoff. The roll program is good. And she's looking fine. Looking real fine. The launch program is in. I'll have the official liftoff time for you in just a moment. Looking real fine on the Doppler plots here. Plotting straight and true. All battery voltages are good. You can hear her rumble overhead. Delta 33 looks fine.
Once in orbit, the automatic picture transmission system began transmitting using a slow scan procedure, only 4 lines per second. This procedure was typically used to transmit radio photographs. All 47 ground stations around the world were able to receive satellite images at the rate of 3 pictures per orbit. This formed the first body of wide-angle imagery ever assembled. True space-based study of Earth had begun. TIROS 8's automatic picture transmission system exceeded its 90-day expected lifetime and was a great success. The spacecraft remained operational for 1,287 days before being deactivated by NASA on July 1, 1967. In total, there were 12 TIROS launches between 1960 and 1966. TIROS began coverage of the Earth's weather in 1962 and was used by meteorologists worldwide. The TIROS program was extremely successful, providing the first accurate weather forecast based on data gathered from space. The program's success with many instrument types and orbital configurations led to the development of more sophisticated meteorological observation satellites. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.